Okay, so if these are the two frame and machine that we have, we need to now look at how we draw the free body diagrams of these. And the trick is, since these aren't composed of two force members, we need to quantify the forces at each of the pins that are in them. So let's look first at the free body diagram if I split this into pieces. The first thing I do is I split it into the three pieces, AC, CE, and then B over to me standing on the diving board. And what this shows us then is that we have three individual pieces that must remain in static equilibrium if the whole thing is to remain in static equilibrium. So if I break it into its pieces, then I need to quantify the forces where they interact with each other. So let's start with AC. I have three pins, AY-AX, BY-BX, CY-CX. Then if I move to CE, E is pretty standard, EX-EY, DX-DY. It's at C that we have to be very careful. And at C we have to make sure that where it interacts, it experiences equal and opposite forces. So if C on member AC is pushing on CE, then CX must be pushing back. Or I should say, if C is experiencing a pull in this direction based on CE pulling against it, then CE must experience a pull in the opposite direction based on CA pulling against it. We can do the same thing with the pliers. We go ahead and we break them into the two pieces, and at the pin we make sure that we draw the forces equal and opposite where they interact with it, where the two bodies interact with each other. Okay? Drawing the free body diagram in frames and machines is actually the bulk of the challenge. The rest of it is actually stuff you're very used to. In this case, we have three rigid bodies, so we could get three sets of three equations. So we'd have 9 equations total that we could use to solve here. Over here, we'd get 6 equations that we could solve because we have two bodies with 3 equations each. Some of the forces in the x, some of the forces in the y, and some of the moments about a point. Okay? So let's take a look at how the book breaks down some free body diagrams. I actually really liked how the book did this. Before they jumped into solving numbers, they just did a bunch of examples where they're drawing free body diagrams in your book. So if you get lost on this, go ahead and read through these examples where you can see, okay, here's two members with pin joints at A and C. We can separate them and draw their free body diagrams like so, and the thing we have to be careful of is where they interact with each other, the forces are equal and opposite. Okay, so then let's look at another one here. Here's kind of a funny frame, right? It's made up of a pulley with a rope going over it, another pulley, rope stabilizing it. And in order to analyze this, we need to break it into all of the individual bodies. But then where the individual bodies interact with each other, we make sure that the forces are equal and opposite. So for instance, we'll have the rigid kind of frame piece. Then we'll have this pulley C and the pulley B as separate free body diagrams. So let's take a look at that. You can see down at the bottom of the page here that they have a free body diagram for the pulley at B and another one for the pulley at C. And notice that CX and CY are equal and opposite to how CX and CY are depicted on the rigid frame. And this is key to being able to solve these problems. All right? So I gave you a new note packet this week. Let's go ahead and take a look at the first problem on that. Okay? So here's the first problem. Get my pins out. All right? And I'd like you, knowing the information we have now, I would like you to pause the video right now and to draw the free body diagram, or the two free body diagrams, I guess, that we would have if we took this apart. Because if we look at this right now, we would have CX, CY, and AX, AY. So we'd have 4 unknowns, and we couldn't solve for that. So we're going to have to break it into member AB and member BC and draw free body diagrams for each of them. So I'm going to ask you, pause the video, and then we'll come back and take a look at what you came up with. All right, so these are the two diagrams I came up with. All right, both of these are correct. Most students, when they first start doing this, would come up with this diagram that I have showing here. Okay, we treat AY, AX, BY, BX for AB, and then in BC we have BX, BY going opposite, and CY, CX. We can solve this because we have 1, 2, 3, 4, 5, 6 unknowns, and since we have two rigid bodies that each have 3 equations of equilibrium, we can get 6 equations with 6 unknowns. Great. However, this is also an appropriate free body diagram because what I've done here is I've noted that member AB is a two-force member. And so that means I know the direction of the force FAB. I've drawn it equal and opposite where it would interact with both parts. So then if I look at member BC, I just have 1, 2, 3 unknowns, and I could solve this with just 3 equations. Okay? And in fact, I could probably solve it even more directly than that if I needed to. So let's go ahead and we can work it both ways. Let's start with this. I'm going to label this as member 1 and member 2. So let's look at member 1. At member 1, we'll sum the forces in the x direction and set them equal to 0. Okay? So we'll have AX plus BX equals 0. Then I'll sum the forces in the y direction, set that equal to 0. I'll have AY plus BY equals 0. Let me scoot this up a little bit so you can see it. And then I can sum the moments about a point. So let's sum the moments, say, about A, and set that equal to 0, counterclockwise being positive. So summing the moments about A, I will have BY times 3 feet minus BX times 4 feet equals 0. Okay, so those were the 3 equations for member number 1. Note that we have 1, 2, 3, 4 unknowns. Okay, so 4 unknowns. So now let's go to the second set of equations, which is going to be for member 2. The same 3 equations, sum of the forces in the x equals 0. So I'll have negative bx plus cx equals 0. I'll have sum of the forces in the y equals 0. I'll have negative by minus 900, just combining the 400 and the 500, plus cy equals 0. Up is positive. And then I'm going to sum the moments about a point. We could choose B or C, doesn't really matter. Let's choose B equals 0. Counterclockwise, I will have negative 400 times 3 minus 500 times 6 plus 9 times cy equals 0. Okay, so now I had 4 unknowns over here. I add cx, that's 5, and cy, that's 6. But I have 6 independent equations with 6 unknowns, and I can solve that. Okay, I'll leave that to you. You could go ahead and do it. Let's go over here now, and if instead I just looked at member 2 over here, I can sum the forces in the x, setting it to 0. So I'll have, let's see, 3/5 FAB plus CX equals 0. I'll have in the y direction 4/5 FAB minus 900 plus CY equals 0. And I'm going to sum the moments about a point, and I'm going to choose to sum them about B because that eliminates this funky angle business. And so now I'll have minus 400 times 3 minus 500 times 6 and plus cy times 9 equals 0. Okay, so there's 1, 2, 3 unknowns and 3 equations. So I could also solve that set of equations to solve this problem. Okay? All right, here's our next problem. It's the classic pair of pliers that I introduced at the beginning of lecture. We have 100 Newton force on these channel lock pliers, and we were curious to find what the clamping force is on this smooth pipe at B, as well as the pin reaction at A. So as usual, we realize, hey, okay, there's a force here, and a force there. That's 3 forces. So this is not a 2-force member, and same thing with the other piece. So we know in order to solve this, we're going to have to break it into its components. So let's do that. I'm going to pause the video. I want you to draw the free body diagram, and then I'll draw the free body diagram. Okay, hopefully you got a free body diagram that looks something like this. Hopefully a little bit better artist than I am, but you can get the idea here. We have 2 individual members that we're looking at. Member 1 is this piece right here, has 100 newtons acting up, pin reactions at AY, AX, and a normal force on the jaw. And then same thing for member 2. Now what we're asked to find is the normal force and AX and AY. So I'm going to ask you, do we need to solve for both simultaneously, or can we get all we need from just one? Okay, the answer is that you can get it all from just one, because there's only 1, 2, 3 unknowns, and we can write 3 equations of equilibrium for this. All right, so I'd like you to do that now. Write the system of equations needed to solve for equilibrium for body 1, and then we'll come back and go over those together. All right, for the first equation, I sum the forces in the x. I'm going to end up with AX minus n cosine 45. In the y direction, I'm going to have the 100 newtons pushing up, plus AY, plus the normal here with the sine 45. Okay. Lastly, so I've got 1, 2, 3 unknowns, so I need to sum the moments about a point, and I choose to sum about A, because that's going to eliminate the most unknowns. And I end up with negative 100 times 0.25, right, because it's going clockwise, plus n times 0.05 because it's going counterclockwise. Now I have 3 equations, 3 unknowns, and I can solve those like this. Okay, hopefully you got similar results. If you didn't, pause the video and work on it until you can see where you went wrong, okay? And we'll do one more before we wrap up for today. All right, our last problem for today is this engine hoist or cherry picker. If we take a look at this, we can see that, let's identify 2 force members first, okay? So anything that just has a force application in 2 locations is going to be a 2 force member. So I think this guy right here, BD, only loads applied at its ends. Same thing with BF, right? Also a 2 force member. Okay, knowing that these are 2 force members, remember, helps us know the direction of the forces that they apply to the other members, GE and EC and AC. Okay, there's a C here, kind of hard to see that maybe, but there is a C. So, is member GE a 2 force member? It's not, because there's a load at G, there's loads at E, and there's loads at F. So 3 locations. Same thing with AC, load at A, load at B, possible load at C. Same thing with EC, load at E, D, and C. All right. So in order to solve this problem, it looks to me like we're going to have to draw 3 free body diagrams. All right. I'm going to go ahead and draw them for you. There you go. I separated them. And now I want you to fill in the forces that are going to be on these 3. All right. So I'll give you a minute to do that, and then we'll come back together and take a look at what you got. All right, so this is how I solved, or how my free body diagrams ended up looking. I have the weight of the engine, the 125 times 9.81. I have the force from member B, FB, that hydraulic cylinder, acting up at F. And then I have a pin at E, so EX and EY. That's going to be my rigid body 1. Rigid body 2 then, at E, I'm going to have equal and opposite, so I make sure that EX and EY are going opposite to the connection with member 1. I'll have FBD going in the direction of member DB, because we decided it's a 2 force member. And then I'll have CY and CX. On the last one, so joint on member 3, I solved for the reaction. You're going to see I didn't actually need to do that, but it's 125 times 9.81 acting up there. FBD, FFB, notice that these are opposite each other, right? And opposite each other to keep it in static equilibrium, equal and opposite forces. And then we have CX and CY in the corner, again, opposite respectively. So now, let's start at member 1 and write a system of equations for the forces here. Okay, we're going to have 3 unknowns right there. So we can actually solve for FFB right off the bat. But we actually need to get this FBD as well, so we're going to have to write a second system of equations. Okay, so go ahead and pause, write the first set of equations, and then write the second set of equations, and we'll come back together. Okay, so for the first set of equations, you should have something that looks like this. Sum of the forces in the x, and again, we're looking at rigid body number 1 up here. So the sum of the forces in the x, we'll have the horizontal component of FFB going in the negative direction. It's going to be the sine of theta here, so you could either do similar triangles or you could figure out what theta is. I chose to go the route of figuring out what theta is. It'd be the inverse tan of 1 over 3 plus EX, some of the forces in the y, similar, and some of the forces, some of the moments about F. And again, I like to sum the moments about something that has an angle to it because it eliminates some trig and it makes it pretty easy to find out what EY is in this case, right? That only gives us the answer for what FFB is, so then we have to go ahead and solve for the second set of equations to find what FBD is. So again, wrote a second set of equations here. All right. So this is the process for solving frames and machines problems. We'll keep working on these. Your homework will be over these. Like I mentioned in lecture, we're going to have our midterm on Monday the 19th, and it will include Chapter 6 and Chapter 7. So on Friday this week, we're going to be starting up in Chapter 7, so please be ready for that. I'd encourage you to work enough of these problems that you can break them into components and draw appropriate free body diagrams correctly 100% of the time. Okay, if you can do that, you can do this, right? So drawing the free body diagram enables you to write the appropriate equations and solve for the values you're looking for. All right, I think that's all we have for today. I'll see you on Friday.